Hello, my dear students. Hello. Hello.
Good morning, sir.
Yeah, good morning. Good morning, all of you. Once again, I will welcome you all for this online lecture series on this microwaves and antennas. We are discussing the last bit of this fourth model, that is the electric dipole. Electric dipole. The last bit will be the one more topic, that will be the thin linear antenna, as well as the radiation resistance of the lambda by 2 antenna. That is the two topics we are going to discuss in this class. Okay, we'll start the class here by uploading the material. What actually the previous the content, the previously we studied, we got the radiation resistance of the short electric dipole of the any length. By using that length you can have the radiation resistance of the dipole, but here the thin linear antenna we are using. For that, we are calculating the radiation resistance as well as the field pattern of that thin linear antenna. The field pattern of this thin linear antenna will be the different, as well as the electric dipole will be the different. Based on this, the current distribution, you will get the radiation pattern in the far field, that will be the E theta as well as the H pi. How the function we are approximating with respect of the dipole, the current distribution. Based on that, we will have the field at the far field distance, that is the E theta as well as the H phi, that we are going to discuss in this today's class. Just I will upload the material and you go through that. You will come to know. If you have any kind of the doubt, just you feel free to discuss. Is it visible?
Yes, sir.
Okay. Previously, we discussed the radiation resistance of the short dipole, as well as the some of the examples of the radiation resistance. The radiation resistance of the short dipole, that is the RR is equal to the 80 pi square into L divided by lambda whole bracket square. Or you can write this radiation resistance, that is after simplification, 790 L lambda square. As the L lambda changing, the radiation resistance will be changing. Means the radiation resistance for the L is equal, or L lambda is equal to the lambda, or the lambda by 2 antenna, or the lambda by 10 antenna. With respect to of that, we have the radiation resistance. For example, the L lambda is equal to the 1 by 10. We have the radiation resistance will be the 7.9 ohm. 7.9 ohm. Suppose the L lambda is equal to the 1 by 2, the radiation resistance will be the 197 ohm. 197 ohm. That is discussed in the previous class. Today we have planned to discuss the thin linear center feed antennas of the different length, as well as the radiation resistance of the lambda by 2 antenna. Which antenna you are calling as a thin antenna? Which antenna you are calling as a thin linear antenna? The thin linear antenna, its diameter will be the very thin, that will be the lambda by 100. Usually length will be restricting to the lambda by 10, but the thin linear antenna diameter will be approximately taken as a lambda by 10. With respect to of that lambda by 10, we have the far field equation. We have the far field equation. With respect to of that far field equation, the current far field equations will be derived based on the current distribution of the thin linear antenna, that we are going to discuss with respect to of this topic, as well as the radiation resistance of the lambda by 2 antenna, that is also discussing in this class. Here What is actually the thin linear antenna? Thin linear center feed antenna of the different length. The thin linear center feed is nothing but it is the balanced antenna. Okay, here the antenna is symmetric. Here the antenna is symmetric about the its polarity. With respect to of this polarity, we have the feeding of the signal. Therefore, the signal distribution in the far field distance that will be analyzed. That will be analyzed and that will be calculated. Based on that, we have the radiation pattern. We have the radiation pattern. Here it is assumed that the antennas are symmetrically fed the center by the balanced two-wire transmission line. The antenna may be any length. Okay, here we have the considering of the any length. Antenna will be the lambda by 2, antenna will be the lambda, antenna will be the 3 lambda by 2. Like this, the various length we are considering for the analysis. But it is assumed that the current distribution is sinusoidal. The consideration we are taking here, the current distribution of this all the antenna length will be the sinusoidal only. The current distribution measurement indicates that it is good assumption provided that the antenna is thin. Okay, which antenna you are calling as a thin antenna? Thin linear antenna. This the thin linear antenna is of the diameter is less than the lambda by 100. You remember this point. The diameter of the antenna, that is the parameter. We have the parameter with respect of the diameter as well as the length. Here the diameter will be the lambda by 100. Both will be in terms of the lambda only. Why? Because the lambda is the known parameter. With respect of the known parameter, we are taking the dimension. We are taking the dimension of the length as well as the taking the dimension of the that diameter. That diameter will be the lambda by 100 or the less than the lambda by 100, as well as the length will be the lambda by 2, 3 lambda by 2, as well as the 2 lambda. This is of the different length. For this, the current distribution of this dipole, we are approximating it is a sinusoidal distribution. Understood here? These are the parameters you need to remember. Based on this remembering, we have the field equation. Based on this approximation, we have the field equation that we are going to calculate here. Example of the approximate natural current distribution of the number of thin linear center feed antenna of the different lengths are illustrated in the figure 6-7. Here the length will be considered, it is the different length. The current are in phase over the lambda by 2 section and in opposite phase over the next. Means at the lambda by 2 we have the in phase approximation, we have the in phase current, as well as next lambda by 2 the phase will be the opposite. Understand here? The next lambda by 2 length, the phase, the current phase will be the opposite, as well as similarly the current phase will be the opposite with respect to of the one more length. Like this, the different length, every lambda by 2, the current will be what here the opposite in phase. Remember this point. As well as we have the one more figure, that is the 6.8. With respect to of that, sir, sir. Okay, we have the one more figure with respect to of that, we have the calculation of the far field equation with respect to of the this symmetrical feeding thin linear center feed antenna of the length L. The retarded value of the current at any point Z, the antenna referred to a point at a distance S. Here the retarded value that is considered as the S, distance will be the S. With respect to of this S, we have the far field equation. What here the memorize this as well as the remember this. Okay, just we have the figure here. Okay, just I will show the figure here. How many figures we have taken here? Here the current distribution of the lambda by 2, at the center it will be having the maximum value, at the end At the end of the pole, it will be the 0. At the end of the pole, it will be the 0. And with respect to of the one more length, with respect to of the one more length, that is the 3 pi by 4 lambda, we have the current distribution that is shown in the figure. As well as the lambda length, we have the current distribution that is shown in the figure. As well as the 5 lambda by 4, the current distribution that is shown in the figure. Like this, the different length of the thin linear antenna, the current distribution that will be shown in this particular figure here. The approximate natural current distribution for the thin linear center feed antenna of the various length. Okay, usually the current distribution will be the sinusoidal, that will be considered as an approximation. That will be considered as an approximation. With respect to of this approximation, we can have the calculation of the far field equation of the E theta as well as the H5. We have the field that is experienced in the distance, in the space. That will be only the E theta as well as the H5. E theta and the H5. Okay, with respect to of that, we are discussing here. Here the current distribution that will be the I is equal to the I naught sinusoidal, sine of the 2 pi by lambda, the L by 2 plus or minus Z into the e raised to j omega t minus r by c. This is the function, this is the equation. This is the equation for the current of that various length. Just you substitute the length will be the L. L is the lambda by 2. L is the lambda. L is the lambda by 4. L is the 3 lambda by 2. L is the 5 by 5 by 4 lambda. Like this, the various length you can take. Therefore, we have the current distribution with respect to of the different length. This is the function. That function will be the sine of the 2 pi by lambda in bracket the L by 2 plus or minus Z. Z is the propagation direction. It may be the positive Z direction or it may be the negative Z direction. Usually we are considering the propagation direction will be the positive Z direction. The propagation direction will be the positive Z direction. With respect to of this positive Z direction, we have the calculation of the far field equation space. Okay, that is in the space. Just you remember this current distribution, that current distribution will be the sinusoidal, which is equal to the I naught sine of the 2 pi by lambda in bracket the L by 2 plus or minus Z, that will be completed e raised to j omega t minus r by c. As the r is increasing, as the r is increasing, it's the distribution will be reducing. It's the field value will be reducing. Okay, just you remember these two equations or you note it down these two equations. We will be calculating the field equations. Here the expression L by 2 plus Z is used when the Z is less than 0 and the L by 2 minus Z is used when the Z is greater than 0. Here the consideration of the infinitesimal length on that particular dipole. With respect to of this infinitesimal length, we have the integration to derive the total electric field or the total magnetic field over the dipole. Here, the antenna is made up of the series of the infinitesimal dipole of the length dz. We are considering only the element of the dz to calculate. The field of the entire antenna may be obtained by integrating the field from all the dipole making of the antenna with the result one means the dipole dz, that will be the having the sinusoidal distribution that is given in the equation number 1. Again the one more dipole, the dz, that will be also the sinusoidal distribution. Again the one more dipole, that will be having the sinusoidal distribution. Like this, the integrating over all the dipole, you will get the total electric field or the total magnetic field. Just you note it down or visualize properly. Understand here, the thin is nothing but its diameter is less than the lambda by 100. Okay. Its diameter will be the less than the 100 and the length will be changing. Lambda by 2, 3 by 4 by 3 by 4 lambda, lambda, 5 lambda by 4, 3 by 2 lambda as well as the 2 lambda. Okay, you consider the one next also. It may be the 4 lambda. It may be the lambda by 10 also. You consider that. With respect to of that, we have the distribution. As the lambda by 10, the current will be what here? The tapers at the center. Tapers at the center is having the maximum peak and is at the taper to the end poles. End poles. As the lambda is increasing, the tapering will be the more and more. Okay, here is the dipole we are considering to derive the equation for the far field, that is the E theta as well as the H5. Understood here, the far field is nothing but the field equations will be the E theta as well as the H5. E theta as well as the H5. Here the length will be the L. L length. Z is the consideration of the dipole. On this Z we have the dz, that is the small element we are considering, and with respect to of the in the distance to the distant point we have the field analysis with respect to of the S parameter as well as the with respect to of the R parameter. Therefore the R parameter is changing the angle based on the S parameter, based on the S parameter. Therefore, the field distribution will be calculating with respect to of this R parameter. Here the relation for the symmetrical thin linear center fed antenna of the length is derived in the far field equation. In the far field, that is also the to the distant point. Here we have the field equation by integrating. Here we have the field equation considering that is the S of R, and S of R is integrating over the sphere. We have the field will be calculating, that is the H of pi is equal to the J in bracket the I naught divided by the 2 pi r in bracket the cos of beta L cos theta by 2 minus the cos of beta L divided by the 2 sin theta as well as the e theta which is equal to the j 60 into bracket I naught divided by the r, the cos of the beta L cos theta divided by the 2 minus the cos of beta L divided by 2 sin theta. This is the pattern. Okay, we are interested for this pattern only. Remember here, the pattern what actually is shown, what actually the shown in this equation, this is the pattern. This is the pattern. Okay, is the bracket, whatever the given in the bracket, that will be the pattern of the field, where the I naught is equal to the I naught into the e raised to j omega in bracket the t minus r by c, t minus r by c, and the e theta you can relate by the 120 pi h pi u. Why? Because we have the intrinsic impedance, that is the relation which is equal to the ratio of the e theta to the h pi u. Therefore we have the e theta is equal to the 120 pi h pi. Here the equation 2, 3 and 3a. Here we have the three equations. One is the this equation, another is the this equation, as well as the one more equation will be the this. Here the 2, 3 as well as the 3a gives the far field H5 and the E theta of the symmetrical center field thin linear antenna of the length L. The shape of the far field pattern is given by the factor in the bracket. Okay, that bracket will be the cosine of the beta L into the cos theta divided by the 2 minus the cos of beta L divided by 2 divided by the sin theta. This is the pattern. Okay, that bracket whatever it is given, that is the shape of the far field pattern, shape of the far field pattern. Here we have the example. Here the example of the far field pattern of the linear center fed antenna. The three antenna of the different length will be considered. Here the three antenna of the different length will be considered. That will be the lambda by 2 antenna. Okay, one will be the lambda by 2 antenna, one more will be the lambda antenna, as well as the 3 by 2 lambda, 3 by 2 lambda. With respect to the lambda by 2 antenna, when the L is lambda by 2, here you substitute the lambda by 2, L you substitute the lambda by 2, and the beta you substitute the 2 pi by lambda. Beta you substitute the 2 pi by lambda. L you substitute the lambda by 2, and beta you substitute the 2 pi by lambda. Okay, the pattern factor becomes E is equal to the cos of pi by 2 cos theta sin theta with respect to of the this lambda by 2 antenna. The pattern will be given, that is the cos of pi by 2 cos theta the sin theta. This is the pattern. With respect to this pattern, you need to determine the beam width. You need to determine the beam width as well as the radiation resistance. Beam width as well as the radiation resistance. For the beam width we are calculating, that is the half power beam width, which is equal to the 0.707 when the field will be electrical or the magnetical. When you are considering the power pattern, it will be the 0.5. When you are considering it is the field, it will be the 0.707. You equate this equation to the 0.707. You will get the theta. You will get the half power beam width. Half power beam width. That will be the pattern appears in the far field distance. Okay. Therefore, here we are determining the just a minute. Okay. Okay. Is it visible?
Yes,
Hello.
sir.
Okay. Here the length we have taken, it is the lambda by 2 antenna. The pattern appears, it is the donut shaped. Donut shaped. For this donut shaped, you need to calculate the radiation resistance as well as the beam width. Therefore, we have the equation that you have to equate it to the 0.707. You will get the theta. You will get the theta. Therefore, from this theta, you will have the 2 theta. The 2 theta equal to the 78 degree. The beam width of the lambda by 2 antenna of this field E equal to the cos of pi by 2 cos theta divided by the sin theta, which is equal to the 78 degree. 78 degree. And similarly, you can calculate the radiation resistance RR. Radiation resistance of the lambda by 2 antenna. RR is equal to the 73 ohm. 73 ohm. That is from the previous equation. That is from the previous equation. That is the yesterday equation. You need to calculate. And similarly, we have the different lambda. One more lambda. You substitute the L equal to the lambda. Earlier you substituted the L equal to the lambda by 2. Now the L is replaced by the lambda. Therefore the theta will be becomes the 2 theta will be becoming the 47 degree. 2 theta will be becoming the 47 degree. And the radiation resistance will be the 200 ohm. Just you understand here, you can relate this as the lambda or as the length is increasing, the radiation resistance will be increasing. As the length is decreasing, the radiation resistance will be decreasing. Okay, you need to have the comment on these results always with respect to of the what you understood. What is the dipole? How the dipole is observed? Why? Because it is based on the observation. With respect of the based on the observation, you have to comment with respect of the appearance. Here the lambda antenna, the radiation resistance will be the 2000 ohm. Similarly, the again the one more length you have considered, that is the 3 by 2 lambda antenna. 3 by 2 lambda antenna. Here the pattern will be like this. Here it will be shown the four main lobes, main lobes, which is in the this quadrant as well as the this quadrant as well as the this as well as the this. Like this, the minor lobe is appears. Minor lobe is also appears with respect of this the xy, with respect of the xy. Here the lobe will be categorized with respect to of the positive, negative, positive, negative. Like this, the positive will be there as well as the negative will be there, and the positive will be there as well as the negative will be there. Here it is the positive as well as here is the negative. Alternative positive, successive, the positive negative lobes will be derived in the far field E theta as well as the H5. Here the radiation resistance. You see here the pattern is drawn. The distribution is also drawn here. That distribution I have shown with respect to of that simulation. That the animation. Here the distribution at the center we have the maximum output. At this point we have the maximum output at this length. At this length it will be the 0. At this length it will be the 0. Like this, the lambda by 2 here as well as the lambda by 2 here as well as the lambda by 2 here. With respect of this lambda by 2, there will be the phase. Here is the phase. Okay, here will be the opposite phase. Here will be the opposite phase. Okay, whatever we told, we have the analysis. We have the analysis. This is of the thin linear antenna. Thin linear antenna. Okay, which one is called as the thin linear antenna, and how the current distribution of the thin linear antenna and how the pattern will be appears in the distant, as well as the field equation. Okay, that field equation is the integration. Okay, integration of the pointing vector with respect of the that small area dz into the d theta d pi o. Therefore, you substitute that, you will get that equation. Okay. We have the again the 2-3 examples. Just you go through that. If you have any kind of the doubt, just feel free to discuss. Again the pattern is given. The pattern is with respect of that pattern. You need to calculate the beam width. You need to calculate the beam width. Okay. Next will be the radiation resistance of the lambda by 2 antenna, which is also the very important. Understand here the radiation resistance of the lambda by 2 antenna. Earlier it was the radiation resistance of the short dipole. Don't confuse here. Don't confuse here. Earlier the radiation resistance of the short dipole, you have derived the equation for the radiation resistance of the short dipole. Now we are deriving the equation for the radiation resistance of the lambda by 2 antenna. Lambda by 2 antenna. Here large yielding the power radiated. This is the in the far field. This is in the far field. The pointing vector, whenever we are considering, the field equations will be analyzed with respect to of the far field. And we are equating this far field equation to the power equated, that is I divided by the square root of the root 2 whole square into the R0. This is the RMS value of the current. RMS value of the current. With respect to of that, we have the calculation of the power. Therefore, we have the equating of these two, you will get the radiation resistance of the lambda by 2 antenna. First, what actually you need to do here? You need to what here the have the equation of the SR, and you substitute the SR with respect to of the field, that may be the magnetic field. SR equal to what? SR equal to the E theta into the H5 complex conjugate. E theta integration, double integration of the 0 to 2 pi, 0 to pi, E theta, real of the E theta as well as the H pi. Real of the E theta as well as the H pi.
ಫೋಟೋ ನೀನೇ ಕ್ಲಿಕ್ ಮಾಡಿದ್ದೇನೆ.
Hello.
ಇಲ್ಲ ಇಲ್ಲ ನಮ್ದು ನಮ್ಮ ದೋಸ್ತ ಫಿಟ್ನೆಸ್ ಯಾಕೆ ಕಡಿಮೆ ತಮ್ಮಕ್ಲೆ.
Hello Prasanna.
ಮೊಬೈಲ್
Prasanna Palkar.
ಮೊಬೈಲ್
What Prasanna? Just understand the concept here. Here we are deriving the equation for the power by considering the pointing vector. Therefore, the power equation will be the 15 I naught square divided by the pi integration of the 0 to 2 pi 0 to pi cos of the beta L divided by the 2 cos theta minus the cos of the beta L divided by 2 whole square divided by the sin theta. It is the field H pi. It is the field H pi. We are considering the H pi. Therefore, you calculating here d pi. Okay, integration is with respect to of the d pi, that is in the range of the 0 to 2 pi, as well as the integration from the 0 to pi is with respect to of the d theta. We have the d theta here that we are integrating here. Therefore, the 30 I naught square 0 to pi cos of the beta L divided by the 2 into the cos theta minus the cos beta L divided by 2 whole square divided by the sin theta. This is the equation. You are comparing this equation to the I naught divided by the root 2 square into the R naught. From this you will get the R naught, that is the radiation resistance. Therefore, equating the radiated power, okay, as given by the equation 2 to the I naught square into the R naught divided by the 2. We have the P equal to the I naught square R naught divided by 2. Therefore, we are in the calculation of the R naught equal to the 60 0 to pi cos of the beta L divided by the 2 cos theta minus the cos of beta L divided by 2 whole square divided by the sin theta into the d theta. It is the radiation pattern. With respect to of this radiation pattern, we are calculating the radiation resistance. Okay, here we have the form. Here we have the sine integral as well as the cosine integral. We are considering this sine integral as well as the cosine integral, which is with respect to of the sine integral si of x, as well as the cosine integral that will be the sin of the x. Sin of the x. Therefore, the sin of the x will be the in the range. It is in the range, that is the 0 to 2 pi. Here the sin of the 2 pi will be the 30 into the 2.44. The sin of the 2 pi, that is the sine of 2 pi. Cosine of the integral. Cosine integral, we are referring it is the sin of the x. Therefore, the cosine integral of the 2 pi will be the 30 into the 2.44. It will be approximated. It will be getting the value that is the 73 ohm. 73 ohm. But the radiation resistance of the thin linear antenna with the sinusoidal current distribution, that is with respect to of the reactance. Reactance will be the 73 plus J 42.5. Understand here. Okay. Here the reactance will be appeared with respect to of the lambda by 2 antenna. Therefore, we need to cancel this reactance. This reactance. What actually we need to consider here? How actually the antenna dimension need to be changed. Once the reactance will be appeared in the far field distance, that is based on the knowing of the radiation resistance or based on the knowing of the terminal impedances, you can reduce the antenna height. You can reduce the antenna length. Based on that, you can have the reduction of the reactance. Based on that, you can what here the make the zero, that reactance will be the zero. Okay, this is what actually the content you need to understand. Okay, again we will be discussing this content in the chapter 18 of this textbook. Okay, if the time permits, just I will convey this. Just you remember, the sine integral is referred as the SI of x, cosine integral will be referred as the sin of the x. Therefore the x will be having the 2 pi, therefore the 30 into the 2 pi, that is 30 into the 2.44, it is of the this value, you will get the 73 ohm. Again the reactance will be appeared, it is the 73 plus j 42.5, therefore you need to cancel the reactive part of the this 42.5. For that you need to reduce the antenna length lambda by 2. With respect to of the reduction of the length lambda by 2, the impedance, you can have the radiation resistance will be the approximately, it will be what here, the sum about the 65 ohm, sum about the 65 ohm. Okay, just to remember and you understand consideration. Based on this consideration, okay, because have we got?
Yes, sir.